Okay, so hi all, good evening and welcome back to the 6th week of live sessions for AI SMPS. And before we get started for today, can you just confirm if I'm audible properly and is my screen visible to everyone? Okay, thanks for confirming. Okay then. So without any further ado, let's get started. So this week we're going to discuss some questions from week 6 that will cover methods like um, WA star, a bit of which we discussed the last time. Then we will have breadth first heuristic search and SMGS as well, which is sparse memory graph search. Okay, and a bit conceptual things related to that we'll be discussing this week. Um, so yeah, without further ado, I think we can get started. So before we get into the different methods that we just mentioned, there's one conceptual question that we'll solve that is related to the monotone condition that you may have come across in the lecture videos. Okay, so I'll just explain the question to you. The question is the question basically gives you a map that is shown in this figure over here, and like the previous maps that we have come across, it's a 10 cross 10. Each of the small blocks or squares inside it 10 cross 10 units in size, and our goal is to go from start node to the goal node. Okay, and there are two possible heuristic functions that we have to choose between based on the monotone condition. One is the Manhattan distance heuristic function and the other is the Euclidean distance heuristic function. Okay, and we have to choose among these options that tell us whether the monotone condition is satisfied or not satisfied in case of both of these heuristic functions. Okay, so does anyone remember what the monotone condition was that you may have come across in the lectures? Okay, if not, let me just give a simple refresher. So consider we have two nodes M and N. Okay, and there is an edge connecting M and N where the direction of the edge is towards the goal node. Okay, so this G is some goal node and we have some edge going from M to N in the direction of the goal node. Okay, so HM would be the heuristic value estimate at the node M. Okay, and HN would be the heuristic value estimate at node N, whereas KMN would be the actual cost of going from M to N. So the monotone condition tells us that for every such node M and N, the difference of the heuristic value between HM and N should be less than or equal to the actual cost of going from M to N. Okay, so this is the monotone condition in a nutshell. Okay, and based on this, I'll shift back to the question. You have to answer this question over here. So I'll give you a couple of minutes and then we can discuss the solution. In the meantime, if you have a solution, you can feel free to write in the chat box or unmute yourself and then we can take it on from there. Okay, so we already have a couple of answers in the chat box. That's good. So the options we have till now say that both Manhattan distance and Euclidean distance satisfy the monotone condition. So I'll give you a hint. I'll say that you're right about one of those. So um, so one easy way to test whether the monotone condition is satisfied or not is to find a particular edge or a pair of nodes that doesn't satisfy the monotone condition. Okay, so I'll ask you to look for such pair of nodes that violate the monotone condition, both in the case of Euclidean as well as Manhattan distance. Okay, try to think about it. You may have to spend some time trying to find out the actual Euclidean distance heuristic value and the Manhattan distance heuristic value for each of the nodes. But I'll give you one more hint. Focus on these lower edges. Okay, take into account this edge that has weight 55 at the bottom and the one that has a weight 100 towards the bottom of the map. Okay, look at these two specific edges and see if the monotone condition is satisfied in case of Manhattan distance and Euclidean distance. Okay, so I guess let's have a look at the solution. Okay, and that will probably help you get some intuition. Okay, I hope you can see my screen and I hope it's pretty visible. It's not, I hope it's not too small. Maybe I'll zoom in a bit. Okay, so let's consider the Manhattan distance heuristic value function first. Okay, so I have all these pre-computed heuristic function values for each of the nodes, and like I said, we should focus on this one first and then the 101 as well. But let's look at this one first. Let's name this as M and let's name this as N. Okay, so what would be h of M minus h of N? Can anyone tell me? Am I audible? Okay, thanks Rahul. So yeah, so this would be 170 minus 110, that gives us 60. Okay, but you see 60 is greater than the actual cost of going from M to N, which is 55. And what does the monotone condition tell us? That HM minus HN should be less than equal to the actual cost, right? But this is clearly violated in this case, right? 60 is greater than 55. So just because of this one edge itself, we can say that the monotone condition is not satisfied in case of Manhattan distance heuristic function. Okay, whereas if you look at the Euclidean distance, I'll leave it on screen over here for you to verify yourself, or convince yourselves. Now we can take different edges that you have over here, different pairs of nodes. You'll see that the monotone condition is maintained for each pair of nodes over here, right? So the correct answer is that monotone condition is not satisfied in case of Manhattan, but it is satisfied in case of Euclidean distance. Let's check our answer. So our answer tells us that Manhattan distance heuristic does not satisfy the monotone condition, whereas the Euclidean distance heuristic satisfies the monotone condition. Okay, I'll go back to the solution screen and leave it on there so that you can look at it and convince yourselves before we move on to the next question. And if there are any doubts here, please feel free to let me know. Yes, there are two hand raises. Please feel free to unmute yourselves if they have any doubts. Okay, maybe it was by mistake. No worries. So, are there any doubts in this question? If not, I guess we can move on to the next one. Okay. So some of you might have joined a bit late and missed the first question. That's no big deal. So basically, I'll just give a quick recap of what we did. We wanted to see whether given a map, uh, using different heuristic functions like Manhattan distance versus Euclidean distance, whether each of those satisfy the monotone condition or not. Okay, and the monotone condition is this one. For any given pair of nodes m to n, where the direction of the edge is towards the goal node, the difference of the heuristic values hm minus hn should be less than equals to the actual cost of going from m to n. Okay, this is the monotone condition, which is not satisfied in case of Manhattan distance heuristic value, and it is satisfied in case of Euclidean distance heuristic value. Okay, this is the first question in a nutshell, and I think should be pretty clear to everyone now. So let's move ahead to the next few questions, which will be based on the same map that we have been using for all the last couple of weeks in the live sessions. Okay, so here we are going to look at four different approaches. One would be WA star, okay, one would be BFHS, one would be beam search, which we also covered I think in one of the previous live sessions, and then we would look at SMGS. Okay, so let's start with WA star. And all the conditions that we may have come across in the previous live session still are maintained. Okay, in that we have to start from the start node, you have to go to the goal node. All these costs given over here are the actual costs of going from a node to another. um, for our purpose, we would be using the Manhattan distance as the heuristic value going forward, unless otherwise specified. Okay, at least for today's live session. And each of these small blocks has a 10 cross 10 units in size. Okay, those are the usual conditions that we deal with in this map. Okay, so going to the question, so WA star, the way this differs from normal A star is because of this W, which means that it's a weighted A star method, right? So in A star, if you remember, we used to do a combination of the actual cost and the estimated cost or the heuristic cost, right? G plus H. The difference in WA star is that now we will do G plus W into H. We give a certain weight to the estimated cost or the heuristic value. Okay, and everything else remains exactly same as it is in case of a normal A star method. Okay, so what we have to do is we have to simulate the WA star method and report the fourth, fifth and sixth nodes that will be inspected or explored or refined by the WA star algorithm. Okay, so I'll go back to the map. Okay, remember W is 3 in this case. I'll give you some time to try to solve this, and then we can have a look at the solution. Yeah, beam search was not covered yesterday, but in one of the previous weeks we did cover it. I don't exactly remember which week it was, but um, yeah, I think we did cover beam search, but we will still go through one of the applications of beam search today. I think when we applied it, it was in the context of a SAT problem. Today it was in the case of this map where we have to go from start to goal. Okay, but we will come to that. For now, try to solve it with WA star. And I highly encourage, if you come up with any partial solutions, feel free to write us in the chat box, or if you have any doubts, feel free to unmute yourself. Yes, Rajkumar, the grid is made of 10 cross 10 units. Okay, so I hope you have some partial solution ready till now. Let's have a look at the solution and see in what direction we all were heading. Okay, so yeah, like in the usual A star, we are going to start with our start node, which will be inspected first. So we will write 1 over here, but the cost over here will be, so initially it was f equals to g plus h, right? So g was 0 and h was, can anyone remind me what h was? I think it was 160 or something, right? Okay, I'll shift to the map. No, it should be 160, right? Let me check. So how many squares do we have to move? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. Yeah, so 16 blocks we have to move to go from S to G based on Manhattan distance, and that we are going to multiply by 3, right? Because we had in 3A star or WA star we had G plus 3H, right? So 160 into 3, which will be 0 plus 480, right? So I'm not writing the whole thing down. This would be our first node in the search tree. Okay, and the children of these would be E, J, K and O, like we did in the normal A star case as well, but again their distances will also be defined by this F value, this new F value that we have come across. Okay, so E will be having an F value of, what is the actual cost of going from S to E? It is 40, right? So it will be 40 plus 3 into the heuristic value, the Manhattan distance for node E, which if I remember correctly was 170, right? So this should come out to be, what should this be? 40 plus, okay, anyone tell me? No, Rajkumar. So we are told that W equals to 3. That is given to us in the question. If W equals to 2, then yes, it would be something else. 510. Okay. So that would make it 550. Right. Similarly, we will also have similar blocks for J, K and O. So I have the search tree already prepared. So let me shift to that. Let me zoom in for your ease. Okay, so this is where we are at right now, right? We explored S. Okay, we have 4 children of S, which is E, J, K and O, and out of all of these the most promising looking is K and O. Both of them have F value 420, right? But we will break the tie using alphabetical order, right? So K is alphabetically before O, so we will next explore K. Okay, so K is explored second, and then K has a few children of its own. Those are F, H, L and Q. Okay, and again these also have their own associated costs. Now we have to check the most promising solution out of E, J, O, F, H, L and Q, and the most promising is L with F value 350, right? So we inspect L next, which is why we have a 3 over here. Then we add an H over here. Okay, but then we see that this H has a value of 440, which is lesser than the value of 450 which this partial path from S to K to H had, right? So we will apply propagation improvement like in the last session we discussed. We will cross out this particular partial path because we have already found a better partial path from S to K to L to H with cost lesser than 450. Okay, so next we expand Q, which is the most promising looking solution now with F value for 390, and we keep doing this until we reach the goal node finally. Okay, so this is how we construct the full search tree for 3A star and the given map. And the question asked us to report the 4th, 5th and 6th inspected nodes, right? So those would be Q, R and P, right? So let's check the solution. Those are Q, R and P. Okay, so I'll leave the search tree on here for a while so that you can go through it and convince yourselves of the solution. Okay, and if there are any doubts, please feel free to let me know. Hi Praveen. Yeah, thanks for your query. Yeah, we do have recordings available, and those are the links to those would be there in the Swayam portal. Okay, where you usually have your lecture videos. Somewhere over there, you will also find a link to the live session recordings, both for my session as well as the uh, alternate sessions that happen on Saturday by a different TA. Let me show it to you. So this is the usual Swayam portal, right? Here you have your lecture videos. This is where you'll find the links. Okay. So Rajkumar is asking, should we go back to the previous level Q after finding f value of h? Okay, let's go back to the tree and see. So I suppose you are referring to this particular situation, right? Yes. So it doesn't matter which level you are in, you always have to choose the best looking option from all the nodes that have not been explored yet, unless they have been stopped by propagation improvement, right? That's why when we were at this particular stage, right, when we had to choose from, when we had noted down the children of k, which were f, h, l and q, we chose from e, j, o, f, h, L and Q, and out of all of these, L looked the most promising. That's why we chose L. If for instance J had been most promising, then we would have inspected J next after K. Okay, thanks for the confirmation, Deepika. So I hope there are no further doubts in this question, and we can go to the next question now, which is the breadth first heuristic search. Okay, so how many of you remember the breadth first search? Okay, so there are a few requests for a recap of WA star and a confirmation for the actual path. So let's just do that quickly and then move on to the next solution. So, okay, first about the path. So the correct path that we would have encountered would be SKQRPG. Okay. No, so the thing that you are mentioning over here, SKLH PG, no, this is I think something different. You have to be careful of what the question is asking. Okay, sometimes the question asks us the order in which the different nodes were inspected. Okay, in that case our answer would be first S was inspected, then K, then L, then Q, then R, then P, then G. H was never inspected. Okay, so don't mention H in that case. If you are supposed to, if you are asked in the question to mention the path with the least cost as per WA star to go from start to goal node, then that would be S to K to Q to R to P to G with cost 330. Okay, and now about a quick recap of WA star. So the only difference between WA star and the normal A star is the addition of this weight over here. So in normal A star, what we do is we write this F value as G plus H. The difference in WA star is that we write F is G plus some weight into h, okay, which is 3 in our case. That is the only difference between A star and WA star. Rest everything remains the same. Propagation improvement remains the same. The selection of the next node to be inspected remains the same. We break the ties in the same way. Okay. So that's about it. Okay. I hope there are no further doubts in this question. Cool then. Let's go to the next question then, which is the breadth first heuristic search. So how many of you remember the breadth first search that we studied in one of the first few live sessions? Okay, I hope some of you remember. Okay, I'll assume that most of you remember what it was. So just to give an intuition of what we are going to do over here. So usually when we had to go from the start node to the goal node using a breadth first approach, what we used to do is we used to explore the neighborhood, right? And we used to go in this neighborhood exploration manner until we until we reach the goal node. Yeah, can you please mute yourself if you don't have a question? That will help the others. Thanks. What breadth first heuristic search will do is it will give us an upper bound. Okay, so it will if we have limited resources and we don't want to spend our resources comparing all or looking at all of these elements or nodes in the neighborhood, we will put a cap on it. Okay, so let's say we create a boundary and we only explore those nodes that are within this boundary of breadth first search. Okay, and the way we will be doing that is by using this u equals to 303. Okay, so u is an upper bound. Okay, and let's say this upper bound has been given to us by some oracle or some magician or wizard. Okay, there are ways in practical situations by which you can find an estimate of this upper bound, but then for now, for this question, assume that this is given to you that the upper bound is 303. So the way you will modify your breadth first search is that usually what you used to do is you used to add elements to a queue, right? In case of a breadth first search. Now what you will do is while you are adding elements to the queue, you will look at the f values that those nodes are having. Okay, and if the f value is greater than 303 sorry about that, you will not add that node to your queue or the open list. Okay, and that is what is mentioned over here. BFHS, a variation of BFS, prunes new nodes having f values greater than or equal to u just before adding them to the open list. Okay, so that is the difference between breadth first search and breadth first heuristic search. Heuristic because we are making use of this heuristic value and limiting it with this upper bound provided to us by some oracle. Okay, and the question asks us to report the 4th, 8th and 12th nodes inspected by BFHs and their associated costs. Okay, so again I'll let you try to solve it yourself first before we discuss the solution. Okay, so I'll leave it on here for a couple of minutes. So thanks for your question, Pravendra. So the thing is that these sessions are extra sessions. These are extra to the lecture videos that you already have on Swayam, right? So what I would suggest is that first of all, I would highly applaud you that you, despite having the difference in background, you are wanting to learn about this course and enrolled in the course and trying to learn new things. That's really good. And it's, I would say it's not an issue if your some of these concepts are appearing difficult to you at the moment. Just start from the basics. Okay, try to understand why something is happening in a particular method instead of what is happening. Okay, that will come later. Okay, for example, when we apply a normal breadth first search, what we do is, so what is the, I'll give you an example. Okay, our aim is to go from a start node to a goal node via some intermediate nodes as per the map given to us. There are different ways to do that. One such way is BFS or breadth first search. What breadth first search does is, as the name suggests, it looks at the breadth, right? Breadth or the neighborhood first. Okay, it goes exploring in the neighborhood until it reaches the goal node. There is a variation of the method called depth first search that goes in a particular depth until it reaches the goal node. Okay, so try to understand the intuition behind the methods rather than what exactly is happening in the methods. That will help you understand what we do and why we do automatically, and proceed step by step. And I think that should help you understand the concepts. Other than that, we have this live session as well as the discussion forum on Swayam to help you resolve your doubts. And I would highly recommend make use of the discussion forum. So one thing that I've noticed in all the semesters I've taken the live session is that many people are not even aware of the existence of the discussion forum. So that is unfortunate, but still we can make use of it to the best of our abilities, right? No, not an official WhatsApp group. I'm sure if you'll ask your colleagues, you will find some unofficial WhatsApp group, but that would not have, that would not be maintained by NPTEL and the official authorities. So if you join that group, that would be as at your own risk. But what I would highly recommend is you go to this Q&A over here. Okay, this will lead you to a discussion forum. Many people ask questions over here. Okay, some of these might be common to you and some of your friends as well, so you can gain some of your insights from this question answers as well. You can post your own queries as well, and here they will be answered by the lead TA, which is Bhaskaran sir. Okay, Bhaskaran sir is the person who frames all the questions for assignments and the practice assignments. Other than this, if you need any help, then I am there through these live sessions. Okay, and apart from me, there is another TA that who also conducts live sessions on Saturdays. Okay, so whichever time is convenient to you, you can make use of that. Yeah, there was a hand raise. Please feel free to unmute yourself if you have any query. Sorry. No phone number is mentioned for any TA because that is private, right? So the only way we could connect is through the live sessions or the discussion forum. Yeah. Okay, I suppose the hand raise was by mistake, so I'll open the queue. Okay, so do we have any partial solutions or complete solutions to this third question, the breadth first heuristic search? Okay, if not, that's fine. Let's go over the solution and see if that resolves any doubts. Okay, so again I have the search tree constructed for easy reference. I should mention that all of these search trees have actually been constructed by Bhaskaran sir, and I'm just taking the material that he has prepared, so acknowledgement where it holds true. Okay, so let's start. right? So like in any case, we will start with the S node. Okay, and that's how we generally define elements in the graph, Pravendra. Okay, so if you have seen the lecture videos, you might have come across the concept or the data structures called graphs, right? Graphs are defined by nodes and edges. So if we go back to the question over here, these are the nodes and the connecting lines are the edges. And what we are trying to do is we are trying to find a search tree following this particular breadth first heuristic search. I didn't I didn't mention nearby. Yes, neighborhood nodes, yes, but the catch is that we are limiting the neighborhood nodes which are under a particular upper threshold that has been given to us as 303. Okay. Okay, cool. Then let's go over the solution. So we start with the S node, okay, and the children of S are uh, E, J, K, and O, which basically means that we could go to E, J, K, and O from S, okay, and each of these have some particular F values, right? Using F equals to G plus H formulation that we saw in case of A star. Now, all four of these have F values 210, 220, 180, and 180, all of which are less than the upper bound given to us, which is 303, right? So we allow all of that to be added to the queue. Let's maintain a queue parallelly as well, so that it's easy for all of you. Okay, so at the front would be E, followed by J, followed by K, and then O. Okay, S is already in the closed list now because we already explored it. Okay, next would be E. E would be explored next because it is at the beginning of the queue, right? So E is given number 2 over here, and the children of E, or the nodes that we could go to from E, are A, B, and F. Okay, we won't include S again because it's a breadth first search. And we see that out of these, A and B have a F value greater than 303, right? So we won't add these to the queue, whereas F has value 280, which is less than 303. So we will add F to our queue, and it will be added at the back because it is a queue, right? So elements get added at the back, elements get removed from the front. So let's remove E because we have already explored E. The next element that we're going to inspect would be J because that is at the front of the queue now. Okay, and we'll proceed in a similar manner. We will not add elements that have F value greater than 303, and we will add elements that have value less than 303. Okay, and that is how we will construct the search tree. Finally, we will reach the goal node over here with a cost of 300. Okay, and once again I'll maybe zoom out a bit and I'll let you go through this. Yeah, yeah, you are audible. Please go ahead. Okay, okay. Okay. Yeah, so every week we have an assignment that has a deadline. If the deadline has already passed, I'm afraid there's no way to submit it now, but you can use those as practice. For the coming weeks, I highly encourage that you check the deadline. I think it would be available at somewhere at the upper right corner of the assignment, and you. Yeah. Uh-huh. Okay. Um, so based on my experience in this course, I don't think it's possible to redo the previous assignments. Um, but I think each assignment, that's what I'm trying to think about. Based on my knowledge that I have, which might be half informed because I'm not involved with the logistics of the exam. Um, so some of these assignments or some fraction of these assignments contribute to your final marks, final grades. I am not aware what that exact fraction is. Okay, so I think for that it would be good if you could post this query on the discussion forum so that someone from the NPTEL team who is in charge of handling the exam logistics can address it. Or maybe one of your friends can also address it if they are aware, who are taking the course along with you. Yeah, if any of the attendees right now have any idea about this, please feel free to share it with your friend, or you can write in the chat box, whichever you feel comfortable with. If okay, so Rahul says that it's I think best 8. So yeah, out of yeah, I think there'll be 12 assignments in total, corresponding to 12 weeks, and yeah, should have attended 8. I think two of your colleagues confirmed that. So yeah, I think that sure. No, no issues. Ah, okay, okay, sure, sure. Mhm. Okay, so any doubts in this BFHS search tree? Okay, if not, then that's great. Let's move on to the next method then. Okay, so this question BFHS basically asked us the 4th, 8th and 12th node. So that would be K, H and T. Let's just verify that once. So the 4th node visited was K. The 5th node visited was um, for the 8th node visited was H. That was what was asked in the question, and the 12th node visited was T. Right, so K, H and T with cost 180, 270 and 300. That's what we also have. Moving on to the next method, which is beam search. Okay, so some of you who um, might remember the beam search method from our previous discussions. The is that you start from a goal node, start from a start node, and then instead of exploring all the children or all the nodes that you could go to from there, you explore only the two best looking options at each level. Okay, so instead of having all the four nodes after S, which are E, J, K and O, you would only have the two best looking nodes, because here we are asked to follow a beam width of 2. Okay, if the beam width had been 3, you would have explored the 3 best looking nodes. If it had been 4, we would have explored the 4 best looking nodes. Okay, and how will we decide what are the best looking nodes? That would be on the basis of the H values or the heuristic values. Again, we will use Manhattan distance as the heuristic value. Okay, so that's what the question tells us. You have to simulate beam search using H value and beam width 2, and we would select the best two nodes at each level, irrespective of whether they are better than their parents or not. Okay, we terminate if the new layer is not better than the overall best node discovered so far. Okay, and we have to break ties in the alphabetical order. We have to report the path found by beam search and the cost of the path found. Okay, so I'll again let you try to solve this by yourself, and then we can discuss the solution. Okay, so we already have a solution in the chat box. Thanks, Arya. So let's have a look at the solution now and check the solution basically. Okay, so again I have the search tree prepared, right? So okay, so at the first stage we start with S having H value or Manhattan distance heuristic value of 160. Okay, the four nodes that we could go to from S would be E, J, K and O. Each of them have their own heuristic each of them have their own heuristic values, and the two best looking options at this point are K and O with values H values 120 and 120 each, right? So we will ignore E and J. Okay, we won't expand E and J, we will just expand K and O simultaneously. Okay, and these are all the possible children of K and O together. Okay, now out of all of these together we will select the two best looking options. Okay, so here the two best looking options, so one of the best looking options is L, right, which is having a value of 80, and then the least value after that is 90, which is being shared by H, Q and Q again. Okay, so note that these Q and this Q are different, okay, because they are coming from different parents. Okay, this Q is coming from K, this Q is coming from O, but we will break the tie using alphabetical order. Since H comes before both the Q's, we will expand H next instead of the Q's. Okay, so the two best looking options are H and L. Note here that even though we expanded O, none of the children of O were expanded in the next level or next iteration. Okay, so that is a property of beam search. At every level we choose only the two best looking options, doesn't matter which parent they come from. Okay, again we will expand both H and L, and again we see that I and M are the two best looking options at each stage, okay, with values 50 and 60 respectively. So we will expand those. Okay, and finally when we expand those we will reach at goal node. Okay, and P would also be there. So the two best looking options would be goal node with a H value of 0 and P with a H value of 40. All the other nodes we won't be adding to our beam because our beam width is 2, right? So this completes our search tree, right, expanding two best options at each level, and the final path found would be S to K to H to I to G. Okay, let's check our solution. So we have S to K to H to I to G, and cost is 310, that we can calculate from the map. Okay, so we went from S to K with cost 60, then to H with cost 120, that made 60 plus 120 which is 180, then I which is plus 60 again, so 60 plus 120 plus 60 which is 240, and then we went to G which is plus 70, so 240 plus 70 which is 310. So 310 is the cost of going from S to G via beam search. Okay, I'll go back to the search tree and I'll again zoom out and I'll leave it on here so that you can convince yourselves of the solution. Rajkumar, thanks for your question. So the reason we chose H, which is having higher value compared to L, because our beam width is 2. Okay, so we don't need to have the same value for the two elements in our beam. Okay, we can have different values, just that we need to have the two best looking solutions at that level. And if you look at the third level, H and L are the two nodes having the least H value, right? Q also has 90, but then we don't choose Q because H is coming alphabetically before Q. Okay, that's why we're choosing H and L. Okay, any doubts in beam search? Okay, I hope this also refreshes your memory of the beam search we discussed in the context of the SAT problem. If S is better than the parent nodes, then we recursively go about it. Um, S doesn't have a parent, right? Do you mean to mention any other node here, Srinivas? While you clarify it, maybe I'll answer the other questions. Beam search meant for use only H values. So the current question that we are dealing told us to use only H values. Okay, if it mentions us, if it tells us to use some other way, we would use some other way to evaluate the nodes at each level. Okay, and how did we get E as 170? That is using the heuristic value. Okay, Manhattan distance. We calculated the Manhattan distance of E. Okay, so if you might have seen the lecture videos or the live sessions previously, we basically have to find the Manhattan distance of E, which is essentially the number of these small boxes that we have to traverse to reach from E to G, and that comes out as 17 boxes. Okay, and each box is 10 cross 10 units in size, so we multiply 17 by 10, that gives us 170. Rajneesh, the H value is the Manhattan distance. Okay, so if S is among the children of a node, suppose S happens to be one of the best two nodes, then will we do search recursively again? No, we won't do that. See, K also had S as its node, right? Okay, okay. Sorry, I get your question now. So you mean to say if suppose this S had a smaller heuristic value, then would we go recursively about it? Yes, in that case we will do that. But I think that situation is not, it's not expected to happen very often, I would say. Yeah, thanks for your question. Any other doubts in this question? Yeah, exactly. We are traversing from S using the KHIG path. So this search tree is based on the heuristic value, not the actual cost, right? The actual cost is given in the map to us. And if you go from S to K to H to I to G, you would have to add 60 plus 120 plus 60 plus 70. That will give you 310. Okay, cool. So I hope there are no further doubts in this question. If there are, please feel free to stop me. Okay, so there was one more question about beam search that asked us what is the other node in the beam apart from G at the point when the algorithm terminates. Okay, so in our case the algorithm terminates when we have found the goal node, and at that point we had P in the beam, right? Remember, beam will always have two nodes, two best looking nodes. So in this one we had G and P. Okay, so the answer to this question would be P. Yeah, thanks for muting. Okay, so I suppose there are no further doubts in beam search. If not, I suppose we can move to the next method and the final method for today, which is the sparse memory graph search or the smart memory graph search. These two terms might have been used interchangeably in the assignments and the lecture videos by Professor Khemani. So yeah, I thanks for muting. It would be great if you could mute yourself if you don't have questions. That would help the others. Okay, so Arya asks how can it be P node? So it is P node because remember at each level we are maintaining two best looking solutions, right? And at the final level, what are the two best looking solutions? G having cost 0 and P having cost 40, right? Although we don't need P over here, but P is still a part of the beam, right? It is because you're having a beam width of 2. So apart from G, P is the one element that is contained in the beam. Okay, now coming back to SMGS. So SMGS is essentially a strategy to make a method like, let's say, A star more efficient. Okay, so you might, so the graphs, the maps that we are dealing with in these live sessions and even the assignments, they are very trivial maps, right? If you spend some time, you can manually find the best path without applying any algorithm by just doing um, a check yourselves manually, right? A brute force check. But in practical cases, you might come across situations where you have thousands or tens of thousands or millions of nodes in the graph, right? In that case, manual approach is not recommended, right? And you would also have limited resources, right? Say you have limited memory available to you, so you wouldn't want to keep track of everything that you are exploring at each step of the algorithm, right? Once you have reached a particular stage where you don't have any immediate use or any um really urgent use of the nodes that you already have explored, you might want to get rid of them and free your memory for the next stages of the algorithm. So I'll give you an intuition. So suppose that this is your these are the nodes in your open list at some stage. Okay, let me create a boundary around it. So this is your open list nodes. Okay, and these are some of the nodes that you have already explored. What does that mean? If you have already explored these nodes, that means that they are part of the closed list, right? Now you still have to reach your goal node. Maybe I'll use a different color for that, right? And you're in a situation where you have limited resources. So would you want to store all of these closed nodes with you? No, right? Because you have to make space for the upcoming open nodes that might exist in this area of the search space, right? This is still unexplored. So what SMGS recommends is for each node in the open list, which is this list, you maintain a link to the immediate uh, node in the closed list, which it is connected to. Okay, so you have a link to these set of nodes, this one, this one, this one, and this one, right? And you know that you are not in need of these nodes, so you will just get rid of these. Okay, or you can get rid of these, or you can store only a subset of these in your memory. Okay, and that's exactly what we try to do in SMGS. So our problem was with the closed list, right? So what we do is we divide the closed list into two parts. One is called the boundary and one is called the kernel. Okay, in this example, all of these nodes would form our boundary of the closed list, and all of these nodes would form the kernel of the closed list. If we have to define it formally, boundary nodes are those nodes that are connected to the uh, open list nodes by at least one edge or one connection. Okay, and kernel nodes are those nodes let's say there is a node over here that is connected to some neighbors, and all the neighbors of this node are part of the closed list. Okay, so this is a part of the closed list, this is part of the closed list, this is part of the closed list, and this is part of the closed list. So we will call this node to be a part of the kernel part of the closed. Okay, so this is how we divide the closed list into two parts, boundary and kernel, and then we store only specific nodes in both boundary and kernel depending on the size of kernel that is available to us. Okay, that helps us make our process more efficient. Let's say when we are applying something like the A star method. Okay, so let's try to apply SMGS using A star method on the same graph, the same map. And because we already solved this map using the normal A star method in the previous live session, we already have the search tree constructed from week 5. Okay, and we are going to make use of this during our SMGS solution. So let's get started with that. So initially we have only we have only S. Okay, and what are the nodes that we could go to from S? We could go to E, J, K and O. Okay, let us draw edges from each of these back to S. So don't confuse the direction of these edges with the direction as per map. Okay, the only significance of these edges is that what we mean to say is that once we are at either E, J, K, O, we do not want to go back to S. Okay, we want to have that information with us, with our algorithm, with our method, that makes our algorithm more efficient. Okay, so that's all this arrow tells us. Okay, let's mark S with a different color to say that it has been visited. Okay, so S has been visited already. As per A star, what was the next node that we explored? Anyone? We have the search tree in front of us. As per A star method, which is the next second node that we will explore after S? K. Thanks for your answer. K would be the next node to be inspected, right? Yeah, because it has the most promising F value, and it is also alphabetically before O, which has the same value, right? So next K will be inspected. Let's go back to our SMGS. So we will mark K as visited. Okay, and then we will look at what are the nodes we could go to from K. Okay, so we could go to F, Q, L and H, right? We don't want to go back to S, so we won't bother about that. So the neighbors of K that we have to add are F, H, L and Q. So let's add that. So we have F, H, L and Q. Okay, and similarly let's just draw edges from each of these, which tells us that we don't want to go back to K from either of these nodes. Okay, so now we have explored two nodes as per A star and SMGS. Okay, now which was the next node that we explored after K? O. That's right, the third node to be inspected was O. So we will mark O as inspected, and we will look at sorry, what are the neighbors of O. So the neighbors of O are N, U and Q. Now comes an interesting point where we have a Q again, right? So Q was connected to K before, remember? And O is also connected to Q. Now we have to decide whether we want to keep the connection between K and Q, or do we want to change the connection of Q to O instead of K. Okay, so let's write down N, U and Q first in our graph. Okay, so we have N, U and Q we already have over here. Now let's look at our A star search tree. Okay, Q coming from O had a cost of 200, right? Whereas Q coming from K had a cost of 210. So what will propagation improvement tell us? That we don't need to explore this partial path anymore. We have to update the link of Q from K to O, because this is a more promising partial path, right? So what we will do is we will erase this link between K and Q. We will instead add Q to O. Okay. Okay, why we went for O? We went for O because as per the A star search tree, after K, the most promising looking solution among all the nodes available to us, which were E, J, F, H, L, Q and O, was O with cost 180. Okay, that's why we went for O next. Okay, any doubts until this point? Okay, if not, then that's great. Let's proceed then. So after O, which is the node that we are going to inspect? L. That's right. L is the next node to be inspected with the most promising cost of 190. So we will inspect L next. So L is over here. Let's mark L with a different color to say that sorry, L has been visited. And let's look at what are the neighbors of L. The neighbors of L are K and H only. Okay, so K and H. So K is already visited, so we won't bother about K. What about H? Again, we have to take a look at whether we need to modify the link between K to H, and do we have to make it from H connected to L. Okay, let's have a look at the A star search tree, and we see that the partial path from S to K to L to H has a cost 260, which is lower than the cost of 270, which is from S to K to H. Right, so again propagation improvement will work over here, and we will update the link of H. Instead of being connected to K, it will be connected to L. Okay, is that clear? Okay, cool then. So at this point we have explored or inspected 4 of the nodes in the graph, right? 4 of the nodes that are marked by the yellow color over here, right? And let's go back to the question and see what the question asked us. Okay, so the question asked us that we have to assume that sparse memory graph search has enough memory to hold 4 nodes in the kernel. Okay, so the size of our kernel is 4 nodes. Okay, we will not count S to be part of the kernel because it is never deleted. This is an assumption that you can make about the method, or when you use SMGS. Okay, what we have to do is we have to list the nodes in open after SMGS has inspected the fourth node, where S is the first node to be inspected, and we have to list the nodes in the boundary after SMGS has inspected the fourth node. Okay, so we have already inspected 4 nodes as of now, right? Let's go back to our graph and see what are the nodes in open. Okay, so all these nodes that are in blue color are the ones that are still part of our open list, in which means that they are yet to be explored, right? And all the nodes that we have already visited, we have colored using yellow, those are part of our closed list, right? So the nodes in open list that we have are J, E, N, U, Q, F and H. Okay, the question may ask you to report this in some order, maybe alphabetical order or some other order, but that is a different question. Now we have to look at the closed list. Okay, the closed list that we have consists of S. Let me use a different color. This S, this K, this O and this L. Now we have to divide this closed list into 2 parts, boundary and kernel, right? And as per the definition, the boundary is consisting of all those closed list nodes that have at least one connection to one of the nodes in the open list, and kernel consists of those closed nodes all of whose neighbors are also in the closed list. So do we have any elements in the closed list that could be put into the kernel at this stage? No, that's right. There are no such nodes in the closed list which can be put into the kernel as of now. So all the nodes in the closed list will go into our boundary at the moment. Okay, and our kernel will be empty. Okay, so let's have a look at the solution. Okay, so these are our nodes in the open list, we just saw that, and K, L, O and S are the nodes that are in our boundary, and our kernel is empty. Okay, we can write kernel has nil or no nodes. So this was until 4 nodes were inspected. Okay, as we keep on increasing, we keep on inspecting more and more nodes, we will reach a point where we will have certain elements in our kernel, which is we would have certain elements that have only neighbors that are already in the closed list. So then what we will do is we will put those in our kernel list. Okay, and our kernel size is only 4. Okay, so as long as we have only 4 nodes in the kernel apart from S, okay, because S is already part of the kernel, we never consider it. So apart from S, if there are 4 other nodes in the kernel, our situation is well and good. If there are more than 4 nodes that we could categorize as kernel nodes, we will discard the nodes, the one of those nodes. Let's say we have 5 nodes that we could put in the kernel, but but we can hold only 4 nodes, right? So we will discard the oldest inspected node in that case, right? Because we only have enough memory to store 4 nodes in the kernel. So I'll show you an example. So this is what we did till now. Okay, we use the A star solution from week 5 to determine the boundary and kernel status. Okay, and here the color scheme is slightly different. Here the green nodes are the ones that are in the open list. Okay, and the light blue ones are the ones that are in the boundary. Okay, and boundary plus kernel makes up closed. And again, to reiterate the definition, a boundary node is a closed node that has at least one open neighbor, and a kernel node is a closed node with only closed neighbors. Okay, now this is the stage that we were also at. If we go further, this is what we will get. Okay, so the left figure is with 8 refinements and the right figure is with 12 refinements. Okay, so I'll zoom in a bit. So here you see that we have only S is one of the nodes that has only close neighbors. But even in this situation, we will say that the kernel is empty because, like it is mentioned in the question, we never consider S to be explicitly part of the kernel. That is a given to us. That is a given fact to us. Okay. So at this moment also, our boundary would consist of N, O, Q, J, E, K, and L, and all the green nodes would be in part of the open list, and our kernel would be empty. Whereas after 12 refinements, now we have these dark colored nodes which are part of the kernel, right? So at this point we will say that O, K, and L are part of our kernel. These light blue colored nodes U, N, J, E, F, H, Q, and R, they are our boundary, and all the green nodes are the open list. Okay, so I leave these 8 refinements and 12 refinements on here for a while so that you can go through them, click a screenshot, and explore it at your own leisure. This is the basic idea behind how SMGS makes a process like A star more efficient. Okay, so Khalid asks how to discard with highest H value. No, Khalid, so you can keep track of the element that was added, the timestamp at which it was added to the closed list, right? And then you can remove the one if you are falling short of the space on in the kernel. You can remove the one that is the oldest added node in the kernel and make space for a new added element to your kernel. Okay. Answer should be in clockwise or anti-clockwise. Don't worry about that as of now. For that, you just have to look at the question. If the question asks you to report the answer in a specific manner, in a specific order, follow that. Okay. But as long as you find the correct nodes, order shouldn't be a big issue. Just make sure you read the question properly when you answer the question in the assignment or the exam. Okay. I'll leave this on here for a while. If you have any doubts, please feel free to let me know. Can you please repeat the open list? Sure. So the open list basically is just the elements that we are yet to refine or explore or inspect. Okay, all those nodes form a part of are a part of our open list. Yes, Rajgopalan, all these video session recordings will be shared with everyone. Okay. Like I mentioned to one of your colleagues, they will be uploaded on YouTube and the link will be shared with all of you on Swayam. Okay. Any other doubts in this question? Okay, so there are two queries. Will it be considered wrong if we write kernel list including S? Typically we don't. Okay, but if your question, again, question uh, is the decider. Okay, so if your question says that report S along with the other elements of the kernel, mention S. If the question says do not report S, then do not report S. Okay, the main idea is to get an understanding of how SMGS with A star is working. Okay, how you have to report the answer, that is dependent on the question at hand. Okay, so just go through the question and report it accordingly. Please repeat refinement. So refinement is nothing but inspecting a node. Okay, you look at a node, look at what are the possible neighbors of the node. Okay, add them to your graph and see whether any of those links should be changed depending on propagation improvement. That is what refinement means. Okay, any other doubts in this question? Okay, what is the significance of SMGS? The significance is that it is uh, making our method more efficient when we have limited resources. Okay, suppose you are working on a computer where you can only store 4 nodes in the kernel, right? So it wouldn't make sense for you to try to keep track of all the nodes in your closed list, right? So that's why as we move through the steps of the algorithm, we will get rid of the some of the elements of the kernel which we don't need any longer, right? Because we have limited resources. That's the importance of SMGS. That's why we call it sparse memory graph search, because it is making our method more efficient, more sparse, and also smart memory graph search, because as the name suggests, it is more smart than the usual method. Okay, anything else? If not, I think that brings us to an end of the session. And yeah, yeah, Rajni. So okay, I hope that you have understood the concept of kernel and boundary. If that is so, then that is great. Um, I'm not exactly sure what you mean by inclusion of kernel. Uh, Khalid, no, there will be some time. I have to process the video before I upload it on the channel, right? So there will be some time. Most probably by tomorrow morning, it will be available on the on the respective sources on Swayam as well as on YouTube. Okay. Okay then. Um, Thank you all for attending and have a good evening. And let's meet next week.